Remember, hot and cold are relative terms. You know when water boils, it's very hot, but refrigerant boils at a much lower temperature. So the refrigerant can take on heat, change to a gas, and still seem cold. Again, the reason is because the two substances have different boiling points.
Welcome to Did You Know, the ESCO HVAC show. We will see you in about 45 seconds or so. Make sure that you are subscribing to our channels, our LinkedIn, YouTube, Facebook. Turn on notifications, and we are very excited to be here with you. It's almost time, about 30 more seconds. Make sure to grab your notebook and pen so you can jot down notes along the way, because at the end of the show, you could have an opportunity to ask our guests questions so we can dive a little deeper into these topics. And here we go. Welcome to Did You Know, the ESCO HVAC show. Well, hello everyone. I'm so grateful you're joining us today. We're going to spend some time today diving into a phenomenal topic. And I know I'm like crazy excited. I just got back from the National HVACR Education Conference just a couple of hours ago. It was insane. We had, 1,300. We had a lot of educators there and like 100 classes, and it was very, very long days, but it was so exciting. So this is going to be like a part 2 follow up to an earlier short video I did on clown chemistry, as well as a episode where Eugene and Jason and I were talking about refrigerant molecules. Well, I expanded on that and did a class at our conference where we dove a little bit deeper into that to explore a whole bunch of refrigerants. And so that's actually what we're going to bring to you today. I know, you'd probably rather have me in the clown costume with balloons, but only had a couple hours to get ready, okay? All right, so here we go. Now, thank you all. We really want to know where you're joining in from. Hop in there in the chat. Let us know. Tom, I'm glad you joined us today. I'll have a fun little video to play here in a little while, too. If you haven't seen the balloon chemistry one, actually, you know what? I'm going to go ahead and throw that in there because it's such a cute little video. It's just a short. Sorry, hold on, right? This will set the stage for what we're going to be talking about today. And I think I've got my audio and video all set up. I had to rebuild the studio when I got back because I took everything to Las Vegas. So somebody let me know in the chat if the audio sounds decent. And I'll go ahead and play this little, well, it's like a 1-minute video, and I'll be back. But let me know in the chat if it sounds okay on your side. See you soon. All right, everyone. Are you ready for some balloon chemistry? All right, we took R12, dichloro-difluoromethane, and it had high ozone depleting potential. So we took out one of the chlorine, and we replaced it with a hydrogen and got monochloro-difluoromethane, R22. Still had some ozone depleting potential, took out the chlorine, replaced it with a hydrogen, got difluoromethane, R32. Mildly flammable, we weren't quite ready for that. So we blended it with some R125, and voila, we get R410A. But what if we took R32 and we blended it with 1234YF? We can actually call it R454B. For more training resources and to compare 22, 410, 454B, and 32, go to escogroup.org. Isn't that cute? I just love that little video. Man, we have got a crew today. So I am just absolutely blessed to see our Did You Know community just growing like crazy. Kaylin, glad that you're joining in here over in Metropolis, Illinois. Howard's on the road. Thank you, Howard, for letting me know that the audio is sounding decent. And Paul, man, thank you. Definitely appreciate that. Ron's joining us. Bruce over in North Carolina. Joe Kakinda, how are you doing, sir? I know I was just so hoping to see you there, but it was so crazy. We wouldn't have had a whole lot of time to hang out. So you and I got to get together sometime, just chatting. Just love to catch up and see how things are going with you. So my voice is still a little wanky. It was getting a lot better, but then, traveling, going from dry, humid, hot, cold, airplanes, it was a little bit crazy. So, all right. Are you ready for this? Okay, so this is one of the periodic table charts that we put together to be able to talk about refrigerants and how refrigerants are developed, what they look like, how we actually will remove some components of those to make new refrigerants. And so this class that I did at our conference, it was very short. It was only about 45 minutes. It's kind of like a round table to talk about it. And I don't know how many people were in the class. I would say it was probably around 250, maybe 300. It was a full big class and it was standing room only. There was people out in the hallway. And it was probably the thing that people asked me about the most during the entire conference. And so I wanted to share that with you. And so if you have questions along the way, let me know. I'll stop because it's just going to be me today. Because I wanted to kind of feel like the class that I put on for everyone, just to give you an idea of what it's like at our conference. All right, so here we go. So we're going to start with ground zero. Looking at our refrigerants and understanding that, we've only got a handful of chemicals that we work with. Kevin, thank you so much for hopping in here with us. Yeah, absolutely. Oh, South Africa too, as well, Kevin. Thank you so much. All right, so when we look at the periodic table, we really are only working with four primary elements to come up with all of our synthetic refrigerants that we know of, from CFC all the way to HFO, right? And even when we look at our hydrocarbons, it's still the same. It's just hydrogen and carbon. Now, when we get into things like CO2 and ammonia, we're going to move things around a little bit. But a majority of the refrigerants that we know all come from one same construction, right? And I am going to actually have to grab a separate screen. Not sure why that presentation didn't hop in here. I just had that sucker loaded. So I'm going to throw it back in real quick. And there's a couple slides in here. When I downloaded it from Canva and brought it in, some of the elements, some of the letters on the molecules might be off a little bit, but overall it's in pretty good shape. And I'm going to clean this up and pass it out, because I must have had 50 or 60 people that asked if they could use this PowerPoint presentation in class to go over refrigerants. So this is something that you'll probably be interested in, but I want to make sure I get it cleaned up before I send it out to everyone. Murph, thanks for joining us. Sorry we missed you, but I know taking care of everything at home, and we're glad that you are doing that. All right. So let's start from kind of like ground zero, and let's talk about refrigerants and the construction of refrigerants and how we make new ones off from their base construction. So it really all goes back to the design of the molecule. David, man, joining us from Kenya today. This is really cool. And I didn't do any advertising or any type of promotion on this. So this must be a topic that people are very interested in, because I just put it out late last night, actually. So grateful you're all in here. Okay, so when we start talking about the construction of refrigerants, we're really going to start with the base design. Like, how are all of these elements put together to come up with a molecule? So when we look at this particular one here, this is actually in pentane, right? It is a hydrocarbon, starts with 5 carbons, and we've got our 12 hydrogens attached to that. That pentane design is because we have those 5 penta, right? We have those 5 carbons at its base. It's going to be very important to follow this as we start creating new refrigerants off from these base molecule designs. So if we look at R601, that has a GWP of less than 1, has an ozone depleting potential of 0, and it has a ASHRAE designation of A3. So it's a highly flammable refrigerant. Actually, it would make a fantastic refrigerant to work with. The downfall is that high flammability. So what if we started with pentane and we removed 1 carbon and 2 hydrogens? When we do that, we're actually going to form a new molecule called R600, not to be confused with R600A. We're going to cover that later in the show. R600, we know that as butane, okay? Now, when you look at that, when we simply remove that 1 carbon and 2 hydrogens, created this new molecule, it still has the ODP of 0. It's still an A3, highly flammable, but our GWP actually went up a little bit. We went from less than 1 to 3. Well, what if we did that again? What if we removed another carbon and 2 more hydrogen? What would we end up with? Well, there's that R290 propane, right? And that's got a similar GWP. It's around 3. It has an ozone depleting potential of 0, highly flammable. We're actually going to be seeing a lot of R290 going into commercial refrigeration equipment. It's a very good refrigerant. The only downfall with it, it's highly flammable. Okay, are you ready? So what if we remove another carbon and 2 more hydrogens? Now we're getting down to ethane, R170. Still an A3 highly flammable, has an ODP of 0. Our global warming potential does go up a little bit though. So now we have a GWP of around 5.5. Okay, so these are all just different generations of hydrocarbon refrigerants. Okay, ready? This is where the fun begins. This is the one that blew my mind. Okay, and this from the next slide on, it was the creativity of Eugene Silberstein and Carter Stanfield sitting in their classes and really rethinking what I thought I knew about refrigerants. If I take away 1 more carbon and 2 more hydrogen, I actually start with a base molecule called methane. R50. It's a very good refrigerant, still has a ODP of 0, has that ASHRAE flammability, that ASHRAE designation of A3. It's highly flammable, but our GWP has went up a little ways, right? We're getting down to a core compound. So methane, in some of our early, a lot of our early generations of refrigerants, it was based on this methane design. Not saying it actually was derived from the hydrocarbon methane. Although you're going to see how that methane molecule is utilized as at least the compounds for those. Okay, so let's think about this. If I start with this base molecule, 1 carbon, 4 hydrogen, and I used a chemical reaction, a catalyst, I used some type of a chemical to create a reaction within that. One common one that we use is the process of dehydrogenation. That's where we get a chemical reaction from the hydrogen atoms and we remove them from the molecule, right? Typically an organic compound like a hydrocarbon, in this case, methane. And what happens is we actually end up with a new molecule, but we can also replace those hydrogens that we dehydrogenated from that molecule. Okay. And I hope I'm not going too deep because I mean, this was like way above my head. But after I sit in and started, listening to classes and started reading really good information from both of those, industry authors and just brilliant minds, it really made me see it differently. And then I just kind of went down my rabbit hole. Sometimes I go down a rabbit hole on these things. Well, this was a rabbit hole. This was supposed to be like 15 slides and it ended up at 51 slides. So, but it's very intriguing to me. So what if I took methane and I dehydrogenated one hydrogen out of there and I replaced it with a single fluorine? I have now went from methane to fluoromethane. I added fluorine, removed 1 hydrogen, replaced with a fluorine. I got fluoromethane, R41. ODP of 0, flammability A3. Notice how my global warming potential went up significantly though? So when I removed that hydrogen and replaced it with the fluorine actually caused my global warming potential to go up. And so then I got really curious, right? What happens if I remove 2 hydrogens and replace those with 2 fluorines? Well, then I get R32, difluoro, 2 fluorine with that same methane molecule. R32 is difluoromethane. It has an ODP of 0. And check out what happened to that flammability. It went from that A3 highly flammable into our new classification of A2L. And look at the GWP. As we introduced those fluorines, that GWP went up quite a bit again, went up to 677. We actually introduced this refrigerant back in 1996, but we weren't quite ready for it yet because we had moved from that A3 into that. If you look at it from like R22 to R32, we went from an A1 now into an A2L. And I'll show you how we did that too, how we went from 22 to 32. It's crazy. You're gonna like this. Okay, so we've plucked out 2 hydrogens. We've put back in chemically, we put 2 fluorines in. We got R32. What happens if we do 3 of them? Okay, pull out 3 hydrogen, put 3 fluorine in. Well, now we've got trifluoromethane, R23. Isn't that insane how simple it was to actually get to there? So if when we do this, we've actually ended up with an A1 with an ODP of 0. But because of all of that fluorine, look what happened to our global warming potential. It went up to 12,400. But R23 was actually a very common refrigerant used quite a bit out there in industrial refrigeration applications, right? But man, look at that GWP. Well, what if we replaced all 4 of those hydrogens with 4 fluorines? Anybody got any idea? That gives us a whole new one. That gives us R14. Okay? 4, tetrafluoromethane. Tetra for 4. It has a GWP of 7390, has an ODP of 0, and it has an A1, low flammability, low to no flammability. So simply by dehydrogenating that methane and replacing with fluorine, we actually went through an entire evolution of refrigerants. Okay, are you ready? This is where it just started getting mind-boggling for me. This is why I spent night after night going through every one of these refrigerants to make sure that they were proper, because once I started seeing it, it was just so interesting. All right, there's other processes within chemistry. Another process is called de-fluorination, right? It's a chemical process or chemical reaction where we remove fluorine atoms and we then potentially replace them with something. We don't even have to replace them, but we can replace them with other atoms. So we can use things like enzymes, we can use photochemical processes or electrochemical processes, but we can actually remove those. So let's go back to that R14. Remember, started all the way back with methane, we got to R14. What would happen if we defluorinated R14 and we replaced it with a single chlorine? Then we would have, look at that, R13, chloro, so 1 chloro, trifluoro, 3 fluorines, methane. R13 is chlorotrifluoromethane. It has that A1 flammability, but now check out what just happened. This made so much sense to me when I was able to look at it this way. When we introduced the chlorine atom into this methane molecule, we now have our ozone depleting potential. That's where it came from, right there. Once we defluorinated that and we put in a chlorine, we started adding ozone depleting potential to it. Literally that simple. Now, let's keep going around this clock, right? Wasn't that interesting seeing the whole defluorination? And now we're going to dive deeper into that defluorination. And let's replace 2 of those fluorines with 2 chlorine. Well, that's our R12. That was one of the favorite refrigerants in medium and low temp refrigeration. So we've got the ODP of 1, but now because of the open fluorine, we've got a high global warming potential of 10,200. And so R12 worked for a long time. We started replacing it because of its ozone depleting potential, but also its high global warming potential. All right, so what if we do 3 of those fluorines? Okay, any thoughts? If we do 3 of those fluorines, we replace all 3 of them with chlorine, now we're at R11. So look at that one. So that's an A1, but it still has high ozone depleting potential because of the chlorine, and it has a high global warming potential still, 4,660. But its name, trichloro, so it has 3 chlorine, fluoro, single fluorine, methane. Now, let's keep going, okay? Let's do all 4 of these things. Is this nuts? Like, let me know in the comments if this is starting to make sense, because when I started seeing it like this, it just blew my mind. It just helped me see how refrigerant construction is developed. Okay, so let's replace all 4 of those fluorines with chlorine. Now we get a nasty chemical commonly known as carbon tetrachloride. So if anyone out there have ever heard of carbon tetrachloride, that's actually how we got to it. So we defluorinated with chlorine, and that's what we ended up with. Now, we got high toxicity out of this. It was a nasty chemical. It gets a classification as B1 because remember, the numbers are for the flammability and the letters are for the toxicity. So it turned that refrigerant into a B1 classification, and because of all of the chlorine in it, our ODP went even higher to 1.2. And we have a global warming potential of 1,730. Its technical name is tetra 4, right? Tetrachloromethane. It's still in this entire methane design. But wait a minute. It gets even more interesting from there. Okay, are you ready for this? How about another chemical process? How about a chemical process called de-chlorination? So that is another type of chemical reaction that cleaves that chlorine right out of there. And it gives us the opportunity to replace it. Okay? So what if we started with that carbon tetrachloride or tetrachloromethane, either way you want to call it, and we removed the chlorine and we replaced it with the fluorine? We're right back to R11. That ODP of 1, GWP of 4660. What if we did 2 of them? We're right back to R12 again. Isn't that nuts that we can actually use different chemical processes from the originating methane constructed chemicals, and we can come up with refrigerants a variety of different ways? So now we're back to dichlorofluoromethane. Now, what happened if we took that same methane molecule that we started with carbon tetrachloride? So there we've done 2 of them. What would happen if we replaced one of them with a hydrogen? So we dechlorinated, but instead of putting in fluorine, stayed with that original hydrogen, right? So we'd done a dehydrogenation, we did a dechlorinization. That's R22. Chloro, singular, difluoro, di is 2, methane. Chloro difluoromethane has a flammability of A1, or a classification of A1. It has an ozone depleting potential because there is a singular chlorine in there. It has an ozone depleting potential of 0.055, and it has a global warming potential of around 1,760. Isn't that insane to think that it really is that simple? All right, here we go. It gets better. Believe me, this was a long rabbit hole. This went from like supposed to be a couple days to a couple months. If I remove that other chlorine and put a hydrogen, we're right back to our difluoromethane, R32, that A2L refrigerant that we are now getting very, very comfortable with working with. So when I could see it that way, to know that we can get to the same thing using different chemical processes, it really changed my thought pattern of refrigerants. Because if I replace with 3 hydrogens now, I'm going backwards. Now I'm back to that R41 fluoromethane, and because I have added so much hydrogen into this molecule, this methane molecule, my flammability is right back up where I began, back at that A3 highly flammable. Okay, gets better. I do the 4th one. Now I'm right back to methane, that core chemical of methane with a single carbon and 4 hydrogen. So we started from methane and we dehydrogenated, and then we defluorinated, and then we dechlorinated, and we actually got right back where we started from. It just, when I seen it that way, a lot of us as educators, we're technicians, and as technicians, we're very visual. If we can see something, by golly, there's a very good chance we're going to understand that, right? So in this process, it allowed me to see what we were doing with that methane molecule to get to our different refrigerants. And oh yeah, no, it keeps going. Okay. So that is a whole generation of methane. And there's lots of them. If you go to Wikipedia, you'll see the classifications. If you go to ASHRAE, you'll see all these different classifications. And so if it is a methane, if it ends with methane, you can change all of those in different formulas and you get the refrigerants we just talked about. Well, what if we started with another variation where we simply, instead of having a carbon base, we had a nitrogen base of that same molecule? Look at that. We took methane, CH4, and when instead of using a carbon based, we used a nitrogen base, and that gives us ammonium. That's the household ammonia that we use as like cleaners and sanitizers. B1, because it is slightly toxic. It's non-flammable, but slightly toxic. Ozone depleting potential of 0, global warming potential of 0. Get this. What if I took that household ammonium and I dehydrogenated it, just like we did with that methane? This is crazy. Watch this. That's R717. That is the ammonia refrigerant that we work with the B2 classification, 0 ozone depleting potential, and 0 global warming potential. When I was able to see it that way, it just changed the way I thought about chemistry and refrigerants altogether, because that's exactly what we did. We took ammonium, plain old cleaner that we work with, we dehydrogenated one hydrogen atom off from that sucker, and we ended up with the refrigerant R717 ammonia. Okay, so there's a lot of things we can do in that base, molecule. So let's go back and let's go the other direction. So let's start with methane. Let's now add 1 carbon and 2 hydrogen to that thing. And we're going to get back to R170. Okay. So now we're into a whole nother chain, vertical chain of refrigerants off from ethane, R170, ethane. Okay. So let's dehydrogenate ethane and see what we can come up with. If we replace the majority of those hydrogens with fluorine, we end up with a refrigerant that I've known by name, but I didn't know where it came from. Penta 5 fluoroethane. So the ethane molecule, the 2 carbon and those 6 hydrogen, when we dehydrogenated some of those hydrogen, replaced them with fluorine, we actually ended up with pentafluoroethane. And so we have an entire vertical row of refrigerants based on that ethane molecule. I can use hydrogens, I can use chlorines, fluorines using those 3 chemical processes, and I can get to just about any kind of chemical I want to get to, any type of refrigerant that I want to. But that R125, remember, that is the 1/2 of R410A. R410A is that R125 blended with R32. But that's where it came from. Okay, here's another interesting thing. Is this making sense? Please let me know in the chat. There's still quite a few people. I've lost a couple. I think a couple of them went, no, this is crazy. I'm out of here. Not interested. But there's still a lot of people hanging in. And so if you have questions and this is making sense, please let me know, because I just thought this was absolutely fascinating. Okay, so we're right here. We're in this ethane molecule. Let's do something else to it. Okay, let's add another carbon and 2 hydrogens from that original ethane. Well, that gets us up to propane. So propane is that base for a whole nother generation of refrigerants. The exact same way, whether we dehydrate. Yeah, I'm telling you, isn't it, Katie? Once I seen this, it was like, and we're just 2/3 the way through. We got a whole bunch more. I'm telling you, this was it was a major rabbit hole, but I loved it. All right. So we start at propane. Propane is that molecule. We can go through a whole generation of refrigerants up or down, depending on if we dehydrogenate that propane or whether we de-fluorinate or we whatever we do, we have this another column of refrigerants based on propane. Okay, so this is the reason there's thousands of refrigerants. So let's start with propane. And we're just going to do a few of them, probably a couple of them that we will recognize. So if we took that propane and we dehydrogenated that thing a little bit, and then we used a chemical reaction to take one of those strong bonds between those carbon atoms and we break it into two weaker bonds called an olefin, that's actually where R1234YF came from. So if you look at the name of R1234YF, tetra, there's our four, tetrafluoro, so 4-fluorine, and propene, because it came from that propene molecule of 3 carbons and those 8 hydrogens. So you can always tell by the end of its name where it began from. So with the propene, that is our 3 carbon base. So when we dehydrogenated propene and we used a chemical reaction, or I don't know exactly what created the olefin bond. It would be fascinating to talk to a chemist to see how they went from a singular bond to that olefin bond chemically, but I don't need to know that. It's just another one of those rabbit holes. But now I can see where R1234YF came from. R1234YF is a hydrofluorocarbon. It's an HFC. The olefin is the bond between those 2 carbon atoms. That's why we now have a new generation of refrigerants, because it has changed. So I'm glad you like that. So it's very intriguing. That's why I wanted to share this, because there were so many people that sat through it and went, "Oh my gosh, I can actually see that," and it's starting to make sense. Okay, so there's 1234YF right out of that propene molecule. So let's take that propene and let's just move 1 fluorine and 1 hydrogen. Look at that. Where we had a hydrogen on the right and the fluorine in the center carbon, if those would have been dehydrogenated differently, that is R1234ZE. That's the cousin of 1234YF. And the reason the 1, 2, 3, 4 stays the same is because the chemical construction is the same. The way that the fluorine and hydrogen are placed is what makes it different. But chemically, we still have the same amount of atoms in the structure. They're just in different locations. So if they're placed in that design, that's the YF. And we'll talk about the YF and that ZE here in a little bit, those isomers, why they're there, right? So 1234YF and 1234ZE are chemically the same. They just have been dehydrogenated slightly differently. Okay. Are we ready? Here we go. We're going to keep going. Okay. So let's move on and let's get into that butane. So we know butane, R600, right? It's used in lighters and a variety of different things. So that's 4 carbon and 10 hydrogens. So let's start with the butane. Now we've got another column of refrigerants from butane. So as we get more complex, the more carbon and the more hydrogen we have, the more variety or variations of that molecule we can actually come up with. So let's start with R600. Now, we start with R600 and we move the bonds. We haven't changed them. We have simply moved them from a line where all of the carbons connect in a row to where the carbons all connect to the 1 carbon. So instead of being in a singular line, we actually now have them connecting to this 1 carbon. So because we changed the way our carbon atoms connect, but we didn't change the chemical composition, it now is an isomer. And so the little letters are isomers. That means that it is the same chemical composition as its cousin, where it originated from. It's just reorganized a little bit differently. So, same amount of carbon, same amount of hydrogens, carbons connected differently, and we get what's called an isomer. So, the difference between 600 and 600A, they both have the same ASHRAE classification, they have the same ODP and the same GWP because they are the same chemically, but bonded, they are slightly different. And so the first generation is given an A. If it was moved to other carbons, they would have given it a different one, like a B or C. So the little letter simply is just a different way that we organize the atoms in that molecule. I was like, wow, all right, that's a lot. And then the next day, I was like, okay, let's go deeper. Are you ready? Okay, so that was to get from 600 to 600A. Now, let's go back here. Let's take that 600. Hey, thanks for joining us. We're glad that you're hopping in here from South Africa. I hope you're interested in this. I hope this is helping things make sense of where refrigerants come from and, how we just use chemical reactions to change them into other refrigerants. Okay, so let's start with that R600. And then now let's put one of those olefin bonds in there. Let's dehydrogenate it. And we didn't replace all of the hydrogens. A couple of them we left out. So we simply went from butane, added an isomer, didn't replace all of the hydrogens, but we replaced some of them with fluorine. And now we can get another variation within this butane classification called transhexafluorobutene. And it has that olefin bond. And so this particular one is called R1336MZZ. And so it is one of these HFO refrigerants, the olefin, hydrofluoroolefin, that originated from that propane or that butane. Remember, it started as butane, but then once we changed it, we went to a butene. So once we changed that bond and went into an isomer. Okay, ready? Here we go. We're going to do this again. So let's now add another carbon and 2 hydrogen, and we're going to get up to N-pentane. Now we've got a whole nother column. Every time we dehydrogenate one of those atoms of hydrogen and replace it with something else, it's a new refrigerant. And we keep on going around until they're all fluorines. And then we can de-fluorinate, and we got a whole nother round of refrigerants. And then we can de-chlorinate, and then we got another round of refrigerants, all based on their core molecule. So the reason I want us to see this one is because it's a way to understand a name, a term that has been introduced into our industry that I don't think has been covered at all. I couldn't find any type of training, any type of education, any type of breakdown on this new word. And it was actually, I seen a lot of posts about this next one that I'm getting ready to go to, but it was incorrectly used. And this is super, super, super important. So I want everyone to follow along, okay? So if we start with N-pentane and we have our 5 carbons and we have our 12 hydrogens, that is R6O1, okay? Now, you are going to start seeing a chemical as part of our equipment that is related to N-pentane, but it is not a refrigerant. It does not have a classification. It started as pentane, N-pentane, and it's in a line, but then the carbon atoms were put into a circle, right? Look at that. There's a line, N, there's a circle, C. So C-pentane is a variation of N-pentane, R601. Its technical name is cyclopentane. So, I didn't put the ashtray on here. It is an A3, highly flammable, because it is a variation of R601, but it's not a refrigerant, but it is going to be on refrigerated equipment. And I wanted to do this so that we can see how easy it is for an industry to get confused on things simply because they haven't had proper education on it. So, I have a challenge for all of you. If anyone has purchased a refrigerator or a chest freezer in the last 2 or 3 years, I encourage you to go take a look at it when you get a chance. So, these are 3 different chest freezers. These are all from my local Lowe's. What caught my attention when I kept seeing social media posts and even educational content that referenced R600A as C-pentane. And it continually says R600A C-pentane. As if it was using, or as if people were using C-pentane as a trade name for R600A, just like we did Puron for R410A when it first came out. And I want us to understand why this is labeled this way so we can understand how this is not correct to say. So let's look at this unit and let's determine what happened for it to get that name. If you look at the top left corner up there, I guess it'd be up that way. If you look at the top left corner, let me blow this up a little bit. That chest freezer has 2 labels on it. It has the white label that says C-pentane, and it has the yellow label that says R600A. If you look at the other chest freezer from a different manufacturer right below it, you will see that instead of saying C-pentane, it actually has the complete name, cyclopentane. And then in smaller print, it actually has the R600A. And then finally, I see where this all comes together on this third freezer. So it's telling you that it is C-pentane, but it should never be confused with R600A. Here's why. When you look at the lower portion of that label, right next to where the UL listing is, you're going to see 2 separate lines for 2 separate products. You're going to see that this household refrigeratop had a misspelling on there. I didn't even catch that before. This listed household refrigerator/freezer has a refrigerant of R600A, otherwise known as isobutane. And the large A is incorrect. It should have been a small a, because that is an isomer of R600. And it has a charge of 105 grams. So this particular piece of equipment is a refrigerator/freezer that uses R600A with a charge of 105 grams in its sealed refrigeration system. And then it uses cyclopentane. Anyone know what that would be for? Look at that. Put it in the chat if you catch it. Case/door insulation gas, C-pentane. So what are we using C-pentane for? Cyclopentane in this particular application. Anybody? Hello? Anybody out there? So if you said that it is for the gas to expand the foam inside of the case and inside of the door, you would be correct. So think about this. Remember how many times I have said that we are going through refrigerant transition and HFC phase down, but many other industries, multiple industries are going through an HFC phase down of the refrigerants. The foam blowing industry previously used things like 134A. Yeah, Bruce. Yay. Where's that at? No, there it is. Yeah, thank you, Bruce. Cyclopentane is the foam blowing agent. Yeah, you're right, Paul. So instead of using 134A, which was commonly used in the past, they were forced to change the gas that they were using that caused the foam to expand. They went from 134A to cyclopentane, a hydrocarbon, an A3 highly flammable gas. So this new refrigerator freezer has two hydrocarbons being used in it that were not in it in its previous generation. It's using one hydrocarbon for the foam blower and it's using one for the refrigeration system. So to state that R600A with a small a is the same as C pentane is incorrect, but now you can understand why. Because honestly, when I first started seeing this sticker, I kind of felt the same way. I assumed R600A had a trade name of C pentane until we broke it down and actually realized that that is not the truth, that it has two separate hydrocarbons, one in the refrigeration and one in the foam. And so that was very intriguing to me. That helped me see what was in it by understanding how it was made. So these next few slides are a very, very short progression through some of the common refrigerant chemicals to show you the molecules that I put on that refrigerant map. Because if any of you need to have this for your classroom, the one that we print off doesn't have R12, but I guess we probably could. The one that we typically print off has R22, 410A, 454B, and 32, so that we can show in the classroom those four generations of refrigerants that we commonly use in air conditioning and refrigeration. This one I just added R12 so that you can see to get from R12 to R22, difluoro-dichloro, we simply replaced one chlorine with one hydrogen. That gives us R22. When we replace the other chlorine with another hydrogen, that gives us R32. So a very, very simple process. So if we go back and we look at this from a refrigerant cylinder perspective, when we start with the base molecule of methane, one carbon, four hydrogen, and we replace that one, or replace the two hydrogen with two fluorine and the other two hydrogen with two chlorine, that gave us our R12. To reduce the ozone depleting potential of R12, we replaced it with one hydrogen in place of one of those chlorine to get R22. Then we replaced the final chlorine with hydrogen to get R32. That R125 is simply that. When we added the two, R32 and R125, that give us our R410A. That's why we charge an R410A cylinder upside down, because it has two refrigerants in it that actually do have different boiling points. There's a little bit of glide in between those two refrigerants. Then if we take and look at that R1234YF molecule, there was that olefin bond, those two red lines. And so instead of having one solid bond, it had two bonds that weren't as strong, and that was the olefin. So if we take that refrigerant, and by the way, that R1234YF is what we've replaced 134A in vehicles with. So all of our vehicles, model year 2025, are required to be a lower GWP refrigerant, and so 1234YF was adopted for those. We actually did our very first one in 2012, and then our light duty trucks went there in 2016. So if we take that 1234YF and we blend it with that R32, that gives us the R454B. So our two primary refrigerants going forward with our new generation of A2L equipment will be either R32 or R32 blended with some 1234YF to give it a new refrigerant, R454B. Remember, all R400 or all 400 series refrigerants are blends. That's what that 4 is for. I didn't mean it to come out that way. So if it starts with a 4, it's a blend of other refrigerants. Guarantee it. Okay, now, another thing that we need to take a look at as kind of a recap. Here, let me blow that up a little bit bigger for everybody. So when we're looking at the lower case, that means it is the isomer. So it is the same chemical composition as its founding refrigerant. It's just formulated a little bit differently because the carbon bonds. So it starts R600, all the carbon are bonded in a line, and if I change a couple and make them connect differently, that creates a new isomer like 600A. Yeah, I hope you're enjoying this, Matt. I mean, I know it's deep. It's a lot of science. This rabbit hole, this was like I can't even call it a rabbit hole. This is like going in an ant hole. I went in one and I just had different branches that I went to, and I kept going down them. And finally, I was like, I got to reel myself back in and put this into something, turn it into some training. So what about the larger case, right? The uppercase ones. So when we look at the uppercase, so 454 is a perfect example of the uppercase letters. The uppercase simply means it's a different blend of the same chemicals. So R454B is approximately, and it's not exact, I think it's 69.1, but we're going to just use approximate. R454B is a approximately 69% blend and a 31% blend of, and we get a lot of questions of, well, why did we go with two different refrigerants? Yeah, I'm glad you're enjoying this, Galen. I mean, once I got through this, it's like, I got to share this with the world. So the reason we have two different refrigerants is because they were made by different chemical manufacturers. R32 is a fantastic air conditioning refrigerant. But what we realized was when blended with 1234YF, we could actually create a generation of refrigerants that can be used for multiple applications. So if we take and change uppercase letter, if we change the percentage of the blends of our refrigerants, we can come up with refrigerants that can be used for other applications. So 454B is part of a series of refrigerants. So there is also 454A and 454C. And you can see right there, they're just different blends of 1234YF and R32, which gives them the ability to be able to be used in things like low temp applications. So you will see new refrigerants or new pieces of equipment being manufactured with a refrigerant that looks similar to R454B, but it's not. It will have a completely different name like R454C or 454A. So when we go forward, just remember that the small letter is an isomer, which means we changed the way we connected the carbon atoms in some form or another. And the large case, it's just a different blend of the same chemicals. And that's really it. I know it's a lot. I mean, it's a whole bunch of things to consider. But if you step back and just simply ask ourselves, well, what is a refrigerant? And previously, I didn't have an answer for myself. I knew I had a variety of refrigerants. I did know that 400 series refrigerants were blends, but I didn't know why there were so many refrigerants. I mean, we literally have hundreds or even thousands of different refrigerants when you go into some of these like ASHRAE or Wikipedia listings. So then when you start seeing where they came from, then you can start getting an idea of why there's so many. And so that was the way that I broke down refrigerants chemically so that I personally have an understanding. If you want to dive deeper into this, I'm sure Eugene Silberstein and Carter Stanfield, two fantastic educators in our industry, either one of them would love to talk to you chemically. Rachel Kaiser would, she a chemist, I'm sure, would dive deeper into how things function like that. This is about as far down the rabbit hole as I want to go because it was enough for me to understand it well enough that I could teach somebody else. I could communicate that. And so I think you could do this in a 200 level class in your program. I think it's a lot to introduce in a 100, like that first year program. But if you have, a 2-year program or more, I think this is applicable to be able to introduce when you get into refrigerants so that someone can understand it. I might be wrong. I might be too far down this rabbit hole. But for me, it was very interesting and it answered a lot of questions for me. Daniel, I'm glad that you enjoyed that. And that's what I was looking for. It's one of those things, anytime you come up with something new, you're like, okay, are people going to like this? Or are they going to go, yeah, that's just too much. That's engineering. We don't need that stuff. For me, I thought it was kind of cool. So, any questions? We still have a few minutes left. I'd be happy to answer anything that I know. And if it's more than I know, I'll be happy to direct you to, other educators in the industry that can help solve those for you. So I'll give it a couple minutes. And for those that didn't make it at the beginning when I showed the little clown chemistry where this came from, oh, Bruce, cool, yeah. I'm telling you. So everyone, Bruce Ernst. If you want to learn more about refrigerant chemistry, how some of these things happen, look him up on LinkedIn. Sorry, Bruce. Didn't mean to throw you under the bus like that. All right. So I'm going to go ahead and play that little fun chemistry video again, just in case anyone needs a very simple one to be able to use in a classroom. Here's that. I'll be right back. And I'll give you a minute to put some other questions or comments or anything into the chat. All right, everyone. Are you ready for some balloon chemistry? All right. We took R12, difluoromethane, and it had high ozone depleting potential. So we took out one of the chlorine, and we replaced it with a hydrogen and got monochloro-difluoromethane, R22. Still had some ozone depleting potential, took out the chlorine, replaced it with a hydrogen, got difluoromethane, R32. Mildly flammable, we weren't quite ready for that. So we blended it with some R125, and voila, we get R410A. But what if we took R32 and we blended it with 1234YF? We can actually call it R454B. For more training resources and to compare 22, 410, 454B, and 32, go to escogroup.org. Yeah, Bruce, I would love to connect with you sometime if you ever want to talk a little bit deeper on chemistry and maybe do a deeper dive into this. That would actually be fantastic, Paul. So glad that you enjoyed that. Galen, you tell me, my friend. Here at the ESCO team, we are here to serve you. We want to know what you would like for us to dive into. If it's a deeper version of the conversation that we had today, absolutely. We will get the right people from the industry to run down that rabbit hole. I actually have a form here. I think it was this one. Nope, not that one. There's the feedback form. If you want to scan that QR, that's actually a form to let me know if there's things that you like, things that you don't like, topics that you would like to be covered. And so I highly encourage you to put that in there, and I'll guarantee I will find the right people from the industry to get those questions answered for you. All right. Well, I think that's about a wrap for the day. We're right at the top of the hour. We thank you all so much for joining us. We'll start diving deeper into these topics as we go. I've already been lining up more guests to be on the show for the rest of the year. Yeah, there we go, Howard. I'm glad that you put that out there. So our conference was an amazing success. We owe it to all of our sponsors and contributors, exhibitors and speakers and co-sponsors. It was just an absolute phenomenal event. I am still just wired from it. Short on sleep, but just overly wound up because of the amount of emotion and excitement and information that I absorbed. So go check out the 2026 conference page. Let me actually get you the website to go to that. You can also give us a call at the office. We'd be happy to answer any questions for you. And then definitely let us know what you would like to learn. And we will bring it to you or we will get you the resources for it. So thank you all for joining. We're just grateful to be part of a community together. And we will see you all again next week on Did You Know? The ESCO HVAC Show. Bye, everybody.